This meeting is being recorded.
Okay, welcome to this lecture today. Well, it's just like what we're going to do today is I thought we'd go over test one from last year, from 2019. So test one from last year covered the same units as test one in our class from this year, units 1 and 2. But I should just inform you that, of course, last year the class took their test in class. It was not an open book test last year. So the types of questions you can expect this year may be slightly different to the ones we're going to cover today, but the topics will be the same. Okay, so you can sort of get a feeling for the topics that we might cover in a test, but maybe you may be asked to do a little bit more work, seeing as this year the tests are open book. Also, you'll notice on screen here that the test was 50 minutes last year. This year it will be a little bit longer, so it will probably be closer to 1 hour 15. So you might get an extra question. So you might see here that there are 4 questions in this test, 1, 2, 3, 4. So this year you might expect that it might be a little bit longer. Having said that, it's always good to get our hands on a new set of questions. So I just wanted to go through this, the solutions to this test with you here in a video. So let's get into it. Okay, so the first question is, answer the following questions about each of the differential equations below. Do not solve the equations, so please read the instructions when you do your test. So we have to answer for each of these differential equations. Is the differential equation linear or nonlinear? What is the order of the differential equation? And if the differential equation is first order, is it separable? Okay, so A here, you can see that, of course, this is a first order equation because the only derivative actually in this case is dy by dx. X is the independent variable, y is the dependent variable, and so the only nonlinear term here is in the independent variable. So in fact, this is a linear equation. And is it separable? Yes, it is. And that is because I can write this as dy by dx equals negative sine of x times y, just taking this term to the right hand side, and then finally I can write that as dy over y equals negative sine of x dx. So it is separable here. I have all the x terms on the left side, on the right side, and all the y terms on the left side. Okay, number B here. Okay, well this is obviously a second order equation because my derivative here is 2, is a second derivative, so second order. It's also linear because, well, there are no y squared terms or nonlinear terms in y, which is the dependent variable. Okay, well, it's not first order, so we don't have to classify it as separable or not. So that was easy. C, well, again, first order. Is this linear or nonlinear? Well, it's actually nonlinear, right? And that's because the independent variable here is t, the dependent variable is x, and we have a nonlinear term here in x, so we have an x squared. But it is first order. It is also not separable. Okay, because if I dx by dt, if I take all the terms to the right hand side that are not derivatives, there's no way I can separate this equation to have all the x terms on the left and all the t terms on the right. So it's not separable. Okay, so this next question, question D here, this is also first order because, well, the only derivative is dy by dt. So that's a first derivative. It's non-linear, of course. because the dy by dt itself is squared, so because we're squaring the derivative of y, it's nonlinear. It's also not separable. And I can show that because if I take the square root of both sides of that equation, I get this. I mean, technically plus or minus, right? But I can't get all the y terms on one side and all the t terms on the other. So it's not separable. First order nonlinear, not separable equation. So I think that one was pretty straightforward. And you should know how to classify ODEs in this way. Okay. Moving on to question 2. So we're asked to express the shown first order differential equation, well in fact it's first order linear differential equation, in standard form. Okay. So, well, what is standard form? Standard form, we usually write this as y prime plus some function of x times y equals some function of x on the right hand side. Okay, so well, the only problem with this question is I have an x squared multiplying the first derivative term when I should be just multiplying that by 1. So I'm going to divide everything through by x squared here, and I should simply get y prime x divided by x squared is 1 over x equals 1 divided by x squared is 1 over x squared. 2x divided by x squared is 2 over x. Okay, so pretty easy there. So you could identify actually p of x is equal to 1 over x, and q of x is equal to, let's write it like so. So I just pulled out a common factor of 1 over x there. Okay, part B is show the integrating factor to the equation in part A is x. So this is a first order linear ODE, so we solve it obviously these first order linear equations using an integrating factor. Well, the nice thing is the test told you that in 2019. Okay, so the integrating factor, if you recall, was defined as the exponential of the integral of p of x dx. So in our case, this is the exponential of the integral of 1 over x dx. Okay, well obviously the integral of 1 over x is just the log of x, and because exponential and logarithm are inverse functions, this is simply equal to x. Okay, so pretty straightforward there. Part C, find the general solution to the equation from part A and identify any transient terms. So there's two parts there. Don't forget there are two parts there. So make sure you read the questions properly. So you may recall from the course, the integration, the integrating factor part of the course, the way to solve linear first order differential equations is like so. The general solution is y of x is equal to 1 over mu, so the integrating factor, times the integral of q of x, so the right hand side of the linear differential equation, times the integrating factor. I guess maybe I should put these x's here, dx, plus, never forgetting your integration constant c naught. So let's write that. C naught is a constant. Okay, so let's substitute in what we have. Okay, so what do we have? We have, so this is equal to, now mu of x equals x. We showed that in part B. So we get 1 over x times the integral of q of x. What was that again? Well, q of x was basically the right hand side of the equation in standard form. So that's 1 over x times 1 over x plus 2. 1 over x times 1 over x plus 2. I didn't need that first bracket. Let's get rid of that. And we're multiplying that by mu of x. So mu of x is just x. Okay. So the x here is going to cancel with the 1 over x here. That's just going to be 1. X divided by x is 1. So we end up with simply that this is equal to 1 over x times the integral of 1 over x plus 2 dx plus c naught. Okay, so those integrals are not too hard, of course. So 1 over x, the integral of 1 over x is just the logarithm of x. If we integrate 2, we get 2x. Plus c naught. Okay, great. So we can take the 1 over x into each term in this equation. So we're going to write this as log of x over x plus 2x over x is just 2 plus c naught over 2. Okay, so this is the general solution. So we found that fairly straightforward. But of course the second part of the equation was asking for transient terms. So remember, transient terms are those terms that go to 0 as, in this case, x gets very large or approaches infinity. Okay, so clearly this, oops, I've made a mistake here. This should be c naught over x, not 2. Sorry about that. So this term here is clearly a transient term, because c naught is a constant. So c naught, a constant divided by x, as x gets really, really, really large, that term is going to go to 0. 2 is a constant, so that is not a transient term. But what about this term here? Well, is this a transient term or not? Both of those, log of x and x, go to infinity as x goes to infinity, right? So we actually have to use something from that we've learned earlier in, well, I think it might be second year calculus, called L'Hopital's rule. Okay, so the limit as x goes to infinity of the log of x over x is equal to the limit as x goes to infinity of the derivative of log of x over the derivative of x. Okay, well, the derivative of log of x is 1 over x. So, well, I should write the limit in here too. So let's write the limit as x goes to infinity of 1 over x divided by 1. So the derivative of x is 1. So therefore this is equal to the limit as x goes to infinity of 1 over x, which is equal to 0. So this is also a transient term. Okay, fantastic. Good. Moving on. Find the general solution to each of the following differential equations. Okay, so starting with A here, what do we have? Well, we have a first order equation, but it's clearly non-linear because the dependent variable is y, and we've got this y squared term in here. Okay, so, well, it's a non-linear first order differential equation, and we can't solve it using an integrating factor. But in fact, if that y squared was not there, then it would be easy to solve that equation, right? And in fact, you may recognize this as a Bernoulli equation. With n equals 2, because the power of y is 2. So what I'm going to do is let u equal y to the power of 1 minus n, which is equal y to the power of 1 minus 2, which is equal to y to the power of negative 1, which maybe let's write that as 1 over y. Okay, so well, you could say u equals, let's write this, u equals 1 over y, or equivalently you could say y is equal to 1 over u. Using the chain rule, we can write dy by dx as dy by du multiplied by du by dx. So what is dy by du, well, y is equal to 1 over u, so dy by du is equal to minus 1 over u squared. So therefore, wherever I see a dy by dx, I'm going to replace it by a minus 1 over u squared times du by dx. Wherever I see a y, I can replace it with a 1 over u. And wherever I see a y squared, I can replace it with a 1 over u to the power of 2, sorry. Okay, so let's rewrite our equation now in terms of u. So dy by dx, I'm going to replace that with negative 1 over u squared du by dx minus y, so minus 1 over u equals e to the x times y squared, so times 1 over u squared. Okay, I want to get rid of this minus 1 over u squared here, so I'm going to multiply by minus u squared, because then I'll get positive u squared over u squared, which is 1 there. So if I do that, I get du by dx plus, if I multiply 1 over u by u squared, I get u equals minus e to the x times u squared divided by u squared. So this is times 1. Okay, so this is the new ODE I get. You'll notice that this is first order linear. So I can actually use the integrating factor method here. Okay, so let's write that. Write the integrating factor. Mu is equal to the exponential of the integral of whatever's multiplying the linear term here, or the u term. So that's just 1. So that's just simply e to the x, right? Okay, and then using the same formula we had before, u is equal to 1 over mu, or e to the x, times the integral of the right-hand side. So the right-hand side is negative e to the x, multiplied by mu, which is e to the x dx, plus some integration constant, c naught. Okay, so let's just rewrite that as e to the negative x. So 1 over e to the x is e to the negative x, times the integral of, well, let's bring that negative outside too. E to the x times e to the x is e to the 2x. Okay, so that's equal to negative e to the negative x. So now I've brought that negative all the way out of that bracket. But actually, maybe I won't do that. Sorry, I'll leave that negative in the bracket. Good. So the integral of e to the 2x is just e to the 2x divided by 2. And I've still got my plus c naught here. I can expand that bracket. U is equal to, well, e to the minus x times e to the 2x is just going to be e to the x. So I get negative e to the x over 2 plus c naught e to the negative x. Okay, so that's the solution in terms of u. In terms of y, recall y is equal to, we said y is equal to 1 over u. So y is equal to 1 divided by negative e to the x over 2 plus c naught e to the negative x. Okay, so that was a Bernoulli equation that we had to solve using that substitution. Part B here, well, now we've got a second order, sorry, keep pushing the button. We've got a second order, well, it's linear because, well, we're multiplying the y and its derivatives by just constants. So it's a second order linear homogeneous ODE with constant coefficients. So we know how to solve this, right? we know how to solve this. We can write down the auxiliary equation, m squared plus 2m plus 1 equals 0. We can put that into the quadratic formula. So, okay, let's do that. So m1 or 2, 1 and 2 is equal to minus b, so minus 2 plus or minus the square root of 2 squared minus 4 times a, which is 1, times c, which is 1, all divided by 2 times a, which is 2. Okay, well this is equal to negative 2 plus or minus the square root of 0, right? Because we get 4, 2 squared is 4 minus 4 over 2. So this is actually just equal to minus 1. So m1 equals m2. We have a repeated real root. Okay, so because we have a repeated real root, we know that we can write the general solution to that ODE in the following way. C1 plus C2 times x times e to the minus x, where the minus 1 here comes from the root minus 1. Okay, and this bit in brackets here, the fact that we have the x in here, that comes from the fact that we had a repeated real root. And if you recall in class, when we have a repeated real root, we use the method of reduction of order to find a second solution, and it turned out all we had to do was have a second term multiplied by x e to the, in this case, negative 1x. Okay, great. So again, this is a good advertisement for remembering the 3 cases for the second order linear homogeneous with constant coefficient case. It's a good argument to why you should be remembering that. Okay, and finally, question 4 here. Use the method of undetermined coefficients to solve the initial value problem. Okay, so here we have again a what do we have? A second order linear. So just check that it's linear, but it is non-homogeneous ODE with constant coefficients. And in fact, it's an initial value problem, right? Because we have some initial values too. So first we'll solve the ODE, and then we'll solve the IVP by using the initial values. Okay, so recall that the general solution to the non-homogeneous case is equal to the complementary solution plus a particular solution. So the complementary solution is found by solving the associated homogeneous problem. Okay, so we've got to solve this here. Well, we want to write down the auxiliary equation here, so m squared plus 4 equals 0. Again, really easy to see here that m1 and m2 are going to be complex conjugates. Okay, so we're going to get 2, well, let's say plus or minus 2i here. There is no real part here, only imaginary, so therefore we simply get y of c is equal to c1 times cosine of 2x plus c2 times sine of 2x. Okay, good. So then for the particular solution, we're asked to use the method of undetermined coefficients. So on the right hand side here, we have a cosine of x. Okay, now we have a cosine in the complementary solution as well, but we're okay because it's the cosine of 2x, not the cosine of x. So these two things, cosine of x and cosine of 2x, can be linearly independent. Okay, they're not causing trouble here. So all we have to do is say, well, my particular solution is going to be a times cosine of x plus b times sine of x. So remember, even though we've only got cosine in the non-homogeneous term, the right-hand side of the differential equation, we still have to include this sine bit here. Alright, so let's take the two derivatives, so yp prime and yp double prime. Okay, well, nothing too hard here, so we get negative a sine of x plus b cosine of x, and then we get negative a cosine of x minus b sine of x. So again, very easy derivatives there. And we want to use these derivatives in the solution. Okay, y double prime plus 4y equals cosine of x. So let's do that. So the first term is y double prime, so we get negative a cosine of x minus b sine of x. So that was y double prime of the particular solution, plus 4 times y, so a times cosine of x plus b times sine of x. So that was y. And that has to equal cosine of x, right? So what we're going to do is we're going to match terms. We're going to match the cosine of x terms, and we're going to match the sine x terms on both sides of the equations. Okay, so on the left-hand side, the cosine terms, we have a negative a term there. We have a 4 times a here, and on the right-hand side, we just have 1. So I can write down an equation that says negative a plus 4a equals 1. Okay, so that's pretty easy to see then. A is equal to 1/3. The sine terms, so in the sine terms we have a negative 1 there, and we have a 4b terms there. So negative b and then 4b there. So already I can see that b is going to have to be equal to 0. So therefore my particular solution is just quite simply 1/3 cosine of x. So finally my general solution, which is the sum of the particular solution and the complementary solution, is just going to be, what was the first one? C1 cosine of 2x plus C2 sine of 2x plus 1/3 cosine of x. So this was the complementary, and this was the particular. So we have the general solution right here, but recall that we actually had some initial conditions too. So those were y of 0 is equal to 0. And what was the second one? I forgot. Let me just check. Y prime of 0 is equal to 1. Okay. So let's use this first initial condition here. So if I do that, I get y of 0 is equal to c1 times cosine of 0, which is just 1, plus c2 times sine of 0, which is 0, plus 1/3 times cosine of 0, which is 1. And we're told that that has to equal the initial condition value, which is 0. So we end up with C1 plus 1/3 equals 0, or in other words, C1 is minus 1/3. Okay, so well, pretty easy there. But now we have to use the second initial condition now. And for that we need to take the derivative of this equation. But again, it's not too hard, right? So y prime of x is equal to minus 2 c1 cosine of 2x plus 2 c2 sine. The first one should be sine. The second one should be the cosine. Minus 1/3 sine of x. Okay. C1 of course is negative 1/3, so we could write this, if I erase C1 and replace it with minus 1/3, I'm going to get positive 2/3. And so now if I look at the value of y prime of 0, this is equal to 2/3 times sine of 0, which is 0, plus 2c2 times cosine of 0, which is 1, minus 1/3 of sine of 0, which is 0, and that is supposed to be equal to the initial condition value, y prime of 0 equals 1. Okay, so simplifying this, I get 2 times C2 equals 1, so C2 equals 1/2. So therefore, my particular solution, my solution, is equal to negative 1/3 times cosine of 2x plus 1/2 times sine of 2x plus 1/3 times cosine of x. So this is the solution to the initial value problem. Okay, so as you can see there, I did that 50-minute test in, I don't know the exact time, but it was roughly half an hour. And I was explaining things in more detail, well, probably in about the right amount of detail that you want to put down on the paper as well during the test. Again, I'll just point out that your test will be slightly longer, and well, I'll be trying to write them for an open book test, right? So it won't be exactly the same as what you've seen today, but it will cover this similar topics. Okay, it will cover anything from units 1 and 2. So if you have any questions about the upcoming test, please let me know, and I'd be happy to answer them to the best of my ability. Thank you very much, and I'll see you in the next lecture.